Our cosmos, for instance, encompasses the Milky Way galaxy, and the nearest galaxy to us is the Andromeda galaxy. We estimate that there are roughly 100 billion galaxies in the observable universe. The Andromeda galaxy has played a crucial role in redefining how we might understand the universe and our position within it. For example, while our galaxy is called the Milky Way, the closest one to us is Andromeda. We approximate that there are around 100 billion galaxies in the observable universe. This revelation provided irrefutable evidence that the universe and the concept of creation do not center around Earth. It shattered the belief that the Milky Way was the only galaxy, indicating that we are merely a tiny fragment of the immense universe. Our comprehension of Andromeda has evolved over the past century, mainly through observations conducted on Earth. However, with advanced tools like the James Webb Space Telescope, JWST, now at our disposal, our perspective has dramatically shifted. Surprisingly, recent data from the JWST has questioned our previous notions about the Andromeda galaxy, presenting a new and enormous puzzle to solve. The JWST has captured extraordinary signals from our neighboring galaxy, leaving leading researchers astonished. Join us as we delve into how the JWST has provided startling revelations about the Andromeda galaxy. The view of the Milky Way has undergone significant changes throughout human history, shaped by our expanding understanding of the universe. In earlier times, when our technological capabilities were limited, the Milky Way appeared as a hazy band of light across the night sky, inspiring various interpretations and myths. It was often regarded as a magical and central element in the cosmological beliefs of different cultures. During the 1920s, Edwin Hubble, an American astronomer, made a groundbreaking discovery using the 100-inch Hooker telescope at Mount Wilson Observatory. Through observations and analysis, Hubble demonstrated that the faint clouds beyond the Milky Way were, in fact, distinct galaxies each containing billions of stars. One of the nearest of these galaxies was the Andromeda galaxy, also known as M31. Andromeda has a rich history of observations extending back hundreds of years. One of the earliest known records of this celestial object can be traced back to the 10th century, when the Persian astronomer Abdul al-Sufi described it as a small cloud in star charts from that period. The importance of these observations lies in the fact that al-Sufi was able to identify this distant celestial entity without the aid of adjustable instruments, relying entirely on his sharp vision and observations. Later, in 1612, a more detailed description of the Andromeda galaxy, based on telescopic observations, was provided by Simon Marius. His work laid the foundation for future astronomers to study this massive celestial structure. In 1764, the esteemed French astronomer Charles Messier classified the Andromeda system as M31 in his famous Messier catalogue, mistakenly attributing its discovery to Simon Marius, unaware of al-Sufi's prior work. For nearly a century following this, astronomers were collectively striving to learn more about this mysterious system, each contributing to the previous discoveries. Before that, Galileo Galilei, an Italian astronomer, fundamentally transformed how we might interpret the Milky Way in the mid-17th century. Using his newly developed telescope, he made pivotal observations that challenged the prevailing Aristotelian cosmology. He found that the Milky Way was not just a diffuse band of light but rather a vast collection of individual stars, planets, and other celestial objects. Through his observations, he demonstrated that the Milky Way was not at the center of the universe as previously believed, but a vast array of stars dispersed throughout space. In 1750, English astronomer Thomas Wright proposed a new hypothesis in his work, A New Hypothesis or New Theory of the Universe. According to Wright's hypothesis, the Milky Way was not an irregular distribution of stars in space but rather a flat layer of stars. He also suggested that a part of this vast structure was our own solar system. While Wright's theory was a step in the right direction in understanding the structure of the Milky Way, it was still constrained by the observational technology available at the time. They still believed that the Milky Way was all there was to it, and considering the limitations, this was not surprising. A significant advancement in understanding the nature of the Andromeda galaxy occurred in 1864, when English astronomer William Huggins made a remarkable observation. He studied the spectrum of Andromeda and noticed that it differed from that of a typical nebula. This paved the way for the galaxy to be recognized for what it truly is. While it is large, the Andromeda Galaxy has a mass estimated to be somewhere between 1 and 2 trillion times that of our Sun, a colossal celestial structure residing relatively close to us in the vastness of space. All the research conducted up to this point suggests that Andromeda is around 10 billion years old, making it very old in cosmic terms. Its age indicates a long and complex history of formation and evolution. One of the captivating aspects of Andromeda's origin is the theory that it formed through the merging of several smaller protogalaxies. This suggests that over billions of years, smaller entities gradually came together under the force of gravity to form the magnificent Andromeda Galaxy we see today. Such cosmic mergers are common events in the universe, shaping the formation and structure of galaxies. For a long time, astronomers thought Andromeda was significantly larger than our own Milky Way galaxy. From an observational standpoint, such a mistake could easily be made because we are in our own galaxy, and seeing Andromeda from Earth makes things look so large that one would easily imagine that nothing could come close to its size. However, that is not the case. Galaxies are enormous systems, and their mass is intricately linked to the distribution and movements of stars, gas, dust, and dark matter within them. Accurately pinpointing these attributes is a challenging task that requires sophisticated observational techniques and meticulous analysis. This kind of information requires modern instruments, which is why the truth is becoming apparent now. Recent research has led to a reassessment of these beliefs. New discoveries have prompted scientists to somewhat lower their estimate of Andromeda's mass while simultaneously increasing the mass attributed to our Milky Way. Thus, the current understanding is that the two massive galaxies are much closer in mass than previously thought. The Andromeda Galaxy's actual dimensions, however, are well established. It is known to extend farther than our own Milky Way, with a grand diameter of around 220,000 light-years. Andromeda surpasses the Milky Way's estimated width of around 100,000 to 175,000 light-years, making it a truly massive celestial entity spanning a vast region of space. This revised perspective also highlights the complexities and challenges of accurately measuring the mass of galaxies. At the core of the Andromeda Galaxy, the extremely massive black hole exerts a tremendously strong gravitational pull on surrounding stars. As these stars orbit around the black hole, they follow curved paths similar to planets circling the Sun in our solar system. At certain points in their elliptical orbits, stars come closest to the black hole, known as the periastron. At the periastron, the gravitational forces are at their strongest, causing the stars to move at their highest speeds. This is when the stars bunch up and become more densely packed in space around the black hole. As they cluster, the stars emit energy as radiation, including visible light and other forms of electromagnetic radiation. The increased concentration of stars and the release of radiation create the brighter point of concentration that astronomers observe in the galaxy's core. The core of the Andromeda Galaxy contains an active galactic nucleus, AGN. An AGN is a highly energetic region at the center of a galaxy, characterized by intense emissions across various frequencies, from radio waves to X-rays. AGNs are powered by the presence of a very massive black hole at the galaxy's core. These supermassive black holes are extremely dense regions in space where a tremendous amount of mass is concentrated within a tiny volume. When astronomers observe active galactic nuclei using advanced telescopes like the Hubble Space Telescope, they notice a fascinating phenomenon. One of the most intriguing features of the Andromeda Galaxy is its AGN, which seems to have 2 points of concentration. There are 2 distinct regions where light and other forms of radiation are emitted more strongly than in the surrounding areas. The brighter concentration is the second point of focus, which is slightly offset from the actual galactic center. Within this region lies the supermassive black hole, which has been estimated to be between 11 to 23 million times the mass of our Sun. Supermassive black holes are believed to be common in the centers of galaxies, including our own Milky Way, and play a crucial role in the formation and dynamics of galaxies. When matter, such as gas and stars, gets too close to a supermassive black hole, it forms an accretion disk around it. This disk of swirling material heats up and emits intense radiation across various frequencies, which is why the AGN is highly luminous. When astronomers observe the active galactic nucleus of the Andromeda Galaxy, they notice a brighter point of concentration near the central supermassive black hole. This feature results from the unique gravitational interactions between the black hole and the stars in its vicinity. The Andromeda galaxy also has another truly interesting feature: a wealth of globular clusters. These globular clusters are dense groups of stars that orbit around the galaxy's center, similar to satellites circling a planet. Andromeda is estimated to harbor around 460 of these dense and ancient clusters, each containing thousands to millions of stars that formed around the same time. The large number of globular clusters observed in Andromeda has provided scientists with valuable insights into the galaxy's evolutionary history. The first direct observation of a globular cluster was made by Galileo in 1609, using his telescope. He spotted an entire cluster of stars, called M22, in the constellation Sagittarius. This was a significant discovery, as it revealed that stars were not evenly distributed throughout space but could form groups. The Andromeda galaxy contains a significant number of globular clusters, much like our Milky Way galaxy. Globular clusters are densely packed groups of stars held together by gravity. These clusters are often found in the halos of galaxies, surrounding the central bulge and disk. In the case of Andromeda, these globular clusters are distributed throughout the galaxy, extending from the central region to the outermost regions. The presence of a large number of globular clusters in Andromeda indicates a rich and complex history of star formation and evolution. Interestingly, some of these globular clusters in Andromeda are believed to be the remnants of smaller galaxies that were absorbed by the Andromeda galaxy through gravitational interactions over billions of years. These interactions likely caused the smaller galaxies to lose their stars and material, leaving behind dense and concentrated clusters that merged into Andromeda's structure. Andromeda's globular clusters exhibit a diverse range of properties, including different sizes, ages, and compositions. Some of these clusters contain older stars, while others may have formed more recently. By studying these globular clusters, astronomers can gain insights into the galaxy's formation history, the processes that shaped its structure, and the different epochs of star formation that occurred over time. As these stars age, they evolve, and their properties change, leading to variations in the color, brightness, and composition of globular clusters. Studying these clusters provides astronomers with a glimpse into the past, helping them reconstruct the evolutionary timeline of the Andromeda galaxy. Globular clusters are not the only fascinating objects in the Andromeda galaxy. The galaxy's halo, a vast and diffuse region surrounding its central disk, contains a wealth of intriguing features. The halo is primarily composed of dark matter, which is matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Within this halo, astronomers have discovered a curious phenomenon known as stellar streams. Stellar streams are elongated structures formed by stars that were once part of smaller galaxies or globular clusters, but were stripped away by the gravitational forces of the Andromeda galaxy. As these stars are pulled away from their original locations, they create long, thin streams that extend across the halo. These stellar streams provide valuable information about the past interactions between Andromeda and its satellite galaxies. By studying the orbits and distribution of stars within these streams, astronomers can reconstruct the history of mergers and interactions that have shaped Andromeda's structure over billions of years. One of the most prominent stellar streams in the Andromeda galaxy is known as the Giant Stellar Stream, which is composed of stars from a smaller galaxy that was disrupted by Andromeda's gravity. This stream extends over a vast region of space and offers a unique opportunity to study the process of galaxy formation and evolution in action. In addition to stellar streams, Andromeda's halo contains a significant amount of gas, including hydrogen and other elements. This gas plays a crucial role in the ongoing process of star formation within the galaxy. As gas clouds within the halo collapse under the influence of gravity, they form new stars, contributing to the galaxy's continued growth and evolution. The interaction between the gas in the halo and the galaxy's central disk also leads to the formation of spiral arms, the iconic features of many galaxies, including Andromeda and the Milky Way. These spiral arms are regions of increased density where new stars are born, and they play a key role in the overall structure and appearance of the galaxy. In recent years, the discovery of gravitational waves has provided a new way to study the interactions between galaxies. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects, such as black holes or neutron stars. When galaxies merge or interact, they can produce gravitational waves that propagate through the universe, carrying information about the events that caused them. In the case of Andromeda, future observations of gravitational waves could provide valuable insights into the history of interactions between Andromeda and other galaxies, including our own Milky Way. As these galaxies move closer together and eventually merge, they will produce gravitational waves that could be detected by advanced observatories, offering a new way to study the dynamics of galaxy interactions. The study of Andromeda has evolved significantly over the past century, from early observations that revealed its existence as a separate galaxy to the discovery of its complex structure and history of interactions. With the advent of advanced telescopes like the JWST, our understanding of Andromeda continues to deepen, revealing new mysteries and challenging our previous assumptions. As we continue to explore the Andromeda galaxy, we are reminded of the vastness of the universe and the complexity of the cosmic structures that populate it. The ongoing study of Andromeda not only provides insights into the nature of galaxies, but also helps us understand the broader processes that have shaped the universe over billions of years.